Hello everyone. This PPT is presented by Group 4. The topic of this presentation is thermal conductivity. Now basically we will be starting with the overview of thermal conductivity. Now what is this thermal conductivity? Thermal conductivity is a fundamental physical property characterizing a material's ability to conduct heat. Some materials, such as metal, conduct heat more readily as compared to others. Now, the materials that don't conduct heat are known as thermal insulators. For example, wood. The physical property describing the rate is the thermal conductivity K. Now, there are in particular four mechanisms of energy transport. First one being molecular conduction, second one being convective transport, followed by diffusive transport and radiative transport. Now we will be discussing mainly here molecular conduction. Now what is this molecular conduction? Heat conduction in fluids via molecular energy transport primarily is the focus of this chapter. Now next is convective transport. Energy transported by bulk fluid motion depends on fluid density rho. Now here the characterizing characteristic is v, velocity of the medium. Next is diffusive transport, which occurs in interdiffusing mixtures radiation where concentration gradients drive energy transfer. Next is radiative transfer. Now in this medium is not necessarily required, unlike conduction and convection. Now we will be studying molecular conduction in bit more detail. Now what is this Fourier's law? Fourier's law relates the temperature gradient with the flux. Now, what is the physical setup and development? Consider a slab of solid material of area A located between two large parallel plates of distance y apart. Initially, for T less than 0, both the plates are at the same temperature. At T equal to 0, the lower plate is suddenly brought to a slightly higher temperature T1 and maintained there. As time proceeds, the temperature profile changes and ultimately a linear steady state distribution is achieved. When this steady state is reached, a constant rate of heat flow Q through the slab maintains the temperature difference T1 minus T0. Now what does this Fourier's law state? It says that Q by A equal to K times T1 minus T0 upon Y, which can be written in differential form as Qy equal to minus K dt by dy, where Qy represents flux, energy flux. Now here on this diagram we can see that how temperature is varying with respect to y coordinate. Now in 3D form for Fourier's law, we can write from our above discussion qx as minus k del t by del x, qy as minus k del t by del y, and qz as minus k del t by del z. Combining all three, which will give us q equal to minus k gradient of t. This is the vector form or the isotropic form. Now K is symmetric second order tensor called the thermal conductivity tensor, used for single non-cubic crystals, fibrous materials and laminates. In anisotropic materials, the heat flux vector does not point in the same direction as that of a temperature gradient. Now next we will define the thermal diffusivity, which is denoted by alpha. Now alpha can be written as K upon rho Cp. Now its dimensions are of length squared per unit time. Now we will be defining some dimensionless numbers related to thermal conductivity. First one being Prandtl number. Now Prandtl number is defined as V by alpha, which can be written as mu Cp by K. Now, if Prandtl number is much less than 1, thermal diffusivity dominates in liquid materials. If Prandtl number is much greater than 1, momentum diffusivity dominates as in oils, and Prandtl number is almost 1 means comparable diffusivity as in gases. Now, it involves only physical properties of the fluids, characterizes relative thickness of velocity versus thermal boundary layers. Next is Peclet number. Peclet number is defined as Reynolds number times Prandtl number, which is defined as L nu by alpha. It is the ratio of convective to conductive heat transfer. High Peclet number means convective dominates over, and low Peclet number denotes conduction dominates in heat transport, and Peclet number is the product of Reynolds number and Prandtl number. It is important in forced convection problems. Now we will be seeing some units for thermal conductivity quantities. Let's begin with QY. Since it is a heat flux, it is quantity per unit volume per unit area per unit time. So it can be written as watt per meter square. In CGS unit, it is defined as calorie per centimeter square second, and we can also see the further units of other quantities in this table. Now, how do we measure the thermal conductivity? Let's understand this through a problem. A plastic panel of area 1 feet square and thickness y equal to 0.252 inch. It was found to conduct heat at a rate of 3 watt at steady state with temperature T0 equal to 24 degrees Celsius and T1 equal to 26 degrees Celsius imposed on the two main surfaces. What is the thermal conductivity of the plastic in calorie per centimeter second Kelvin at 25 degrees Celsius? So how do we know? First we will convert it into CGS units so that our calculations will be more simple. So area 144 inches square is equal to 929 centimeters square. Thickness equal to y equal to 0.252 inch, which is equal to 0.640 centimeter. Heat flow is 3 watt, which can be equated to 0.717 calorie per second. Delta T is 2 Kelvin. Now substituting all the values in Fourier's law, which gives us K equal to 0.459 by 1858, that gives us K equal to 2.47 into 10 to the power minus 4 calorie per centimeter second Kelvin at 25 degrees Celsius. Now next we will study pressure and temperature dependence of K. So we will start with the study of principle of corresponding states. Fluids at the same reduced temperature where Tr is equal to T by Tc, where Tc is the critical temperature, and reduced pressure, which is defined in a similar fashion, have approximately the same reduced properties. So for gases, how is the variation with temperature? As K increases with temperature. For monoatomic gases, K is directly proportional to T to the power 0.5, and for polyatomic gases, K is directly proportional to T to the power n, where n varies from 0.8 to 1. For liquids, temperature dependence, K generally decreases with temperature approximately linearly. For gases, pressure dependence, at pressure less than 10 atm, K is approximately independent of pressure. At high pressure, K increases. For liquids, how does K vary with pressure? K increases slightly with pressure. Effect is small, which can be often neglected. Now on the graph we can see that if we know the reduced temperature and we know the reduced pressure, we can find the thermal conductivity from this graph. Now we will be solving a few questions. Now we'll be solving a question. Estimate the thermal conductivity of ethane at 153 degree Fahrenheit and 191.9 atm from the experimental value K equal to this at 1 atm and 153 degree Fahrenheit. Now, how do we find it? Since a measured value of K is known, we use method 1. First, we calculate reduced pressure and reduced temperature at the condition of the measured value, and then we read Kr from the graph. So Tr is equal to 153 plus 460 by 1.8 into 305.4, which gives us 1.115. Similarly, we calculate reduced pressure and we get the value of Kc from the graph. At 153 degree Fahrenheit and 191.9 atm, we read from the chart that Kr is equal to 2.07. The predicted thermal conductivity then will be K equal to Kr times Kc, which gives us 0.0914 BTU per hour feet Fahrenheit. Next is the theory of thermal conductivity of gases at low density. Now first we'll be beginning with the kinetic theory approach. Thermal conductivity of dilute gases is predicted from kinetic theory. Molecules carry kinetic energy from hot to cold regions via mean free path and collision frequency. Now what is this mean molecular speed? It is the average speed of constituent molecules. What is mean free path? It is the average distance between molecular collisions, depends on the diameter and number. What is this collision frequency? It is the rate at which molecules collide with each other. Next is energy transport. Molecules carry kinetic energy 3 by 2 kT from hot to cold planes. Now for monoatomic gases, K is 5 by 2 mu times Cv, and according to Chapman-Enskog equation, it is K is directly proportional to root T by m divided by sigma square into omega K. Now we'll see some questions. Calculate the thermal conductivity of argon at T equal to 300 Kelvin and pressure equal to 1 atm using kinetic theory, Chapman-Enskog formula. So how do we solve it? Temperature is 300 Kelvin, molecular weight is roughly 40, sigma is 3.542 angstrom, collision diameter, and omega K is omega times mu. So from the figure 9.2 at kT by epsilon, we get it as 0.821. So K, from solving it and putting it in Enskog equation, we get K as 3.97 to 10 to the power minus 5 calorie per centimeters per second per Kelvin. Now next question is estimate the thermal conductivity of molecular oxygen at 300 Kelvin and low pressure. The molecular weight of O2 is roughly 32. The molar heat capacity of Cp at 300 Kelvin low pressure is roughly 7.0 calorie per gram mole Kelvin. From table E1, we find the Lennard-Jones parameter for molecular oxygen to be sigma equal to 3.433 angstrom and epsilon by K equal to 113 Kelvin. At 300 Kelvin, Kt by epsilon is 300 by 113, which gives us 2.655. From the table E.2, we find that omega u is equal to 1.0714, which gives us K to be roughly equal to 6.14 into 10 to the power minus 5 calorie per centimeter second Kelvin. Now follow up, we'll see some more questions. Predict K of gas mixture at 1 atm and 293 Kelvin. Component CO2 whose X is 0.133, O2 whose X is 0.039 and N2 for which X is 0.828. Now how do we solve this question? The data is given in the table. So we calculate we term 1 as CO2 and 2 as O2 and 3 as N2. Now we calculate the parameters which are required according to the table. So we calculate m alpha by m beta, mu alpha by mu beta, and phi alpha beta, and then we sum it over sigma beta to 1 to 3 x alpha phi alpha beta. Now putting all the values in the equation, k mixture equal to alpha equal to 1 to n x alpha by k x alpha k alpha by sigma beta x beta phi alpha beta, we get thermal conductivity of the mixture as 584 into 10 to the power minus 7 calorie per centimeter per second Kelvin. Next is theory of thermal conductivity of liquids. Liquid thermal conductivity is more difficult to predict than gases due to complex intermolecular interactions and dense molecular packing. Several semi-empirical approaches have been developed, few of which we'll be seeing here. Now key relationship, temperature dependence. KT is approximately equal to K naught minus B T minus T naught, linear decrease for most liquids. Exception, water increases up to roughly 130 degrees Celsius and then decreases. Pressure dependence, K slightly increases, which can be usually neglected, and reduced properties. Use TR equal to T by TC and then use the chart to estimate K from critical properties. Now we'll be seeing next question. The density of liquid CCl4 at 20 degrees Celsius and 1 atm is this, and its isothermal compressibility is given by this. What is its thermal conductivity? Now we will be doing it as will be calculating it as del P by del rho at constant temperature, which gives us 7 into 10 to the power 9. Following which we will be calculating thermal conductivity, which gives the value as 0.11 watt per meter Kelvin. Next is thermal conductivity of solids. For metals, it varies from 10 to 400 watt per meter per Kelvin. For non-metals, it varies from 0.1 to 10 watt per meter Kelvin. And for insulators, it is less than 0.1, very low conductivity. Now, according to Weidmann-Friend's law, K by sigma T is equal to L, which is approximately equal to 2.45 into 10 to the power minus 8 watt ohm per Kelvin square. For phonon contribution non-metals, K is 1 by 3 CV V lambda.